In this section, we're going to look at Lewis structures for molecules. We've done a couple of videos looking at ionic bonding where we form a positive cation and a negative anion. Here we're going to explore that concept of sharing electrons in a little bit more detail and what a covalent bond actually means. And then we're going to use this information to draw the Lewis structures for molecular compounds with single and multiple bonds. So we've discussed molecules. We looked at molecules when we looked at polyatomic ions. We looked at molecules in the previous video where we discussed naming molecular compounds. So now we're going to look at what actually is happening when a molecular compound forms. So a molecular compound forms when atoms of two or more nonmetals share electrons and form a covalent bond. This covalent bond is going to be between the valence electrons of the individual atoms, that outermost shell of electrons. Now, a molecule will form when two or more atoms share these electrons. They do not have to be shared equally, and they are going to be shared so that we form a stable octet around each atom. So according to the Lewis model, Lewis was a scientist that developed this model, a pair of electrons in a covalent bond functions in two ways simultaneously. The two atoms share it, and it fills the valence shell of each atom. A major theme in chemistry is achieving a very stable state, a low energy state. So if we can achieve that, then that's how a system will proceed. So let's take the hydrogen molecule, H2. It forms as the atoms move closer and the positive charge of the nucleus attracts the electron of the other atom. It has a shared pair of electrons that form a covalent bond to give each atom a noble gas arrangement of helium. Okay, so you have hydrogen with one electron plus hydrogen with one electron. They're going to come together so that those two electrons can be shared between them. And they are going to be shared, okay, at a certain distance from each nucleus. Right, so those hydrogen atoms will come as close as possible so that the nuclei don't repel each other, but the electrons remain shared between the two atoms. And in this configuration, you're going to have a stable state and achieve the noble gas configuration of helium. So you can see this here schematically in this graph. We have two individual helium atoms that are far apart and they have no attraction. And you can see that they have high energy. Now, as the nuclei attract the electron, so the positive is going to attract this electron, and then the positive nucleus, will attract the other electron. So as those nuclei attract the electrons from the other atoms, they're going to pull these two hydrogens closer together. Then they are going to stop at a certain distance because then the nuclei are going to become repulsive. However, this is the lowest energy state of hydrogen, and therefore it exists as H2 with these electrons shared between them because this is more stable. It's lower in energy. So we can use a representation called a Lewis structure in which we can depict the valence electrons of the atoms and we arrange them to give octets, except for hydrogen, which has two electrons. So the number of electrons a nonmetal atom shares and the number of covalent bonds it forms are usually equal to the number of electrons it needs to achieve a noble gas arrangement. So for example, let's take oxygen. Oxygen is in group 6A. Oxygen has 6 valence electrons. So when bonding to a nonmetal, it needs 2 more electrons to achieve 8, or an octet. So oxygen typically forms 2 bonds. the shared electrons or bonding pairs are shown as two dots or a single line between atoms. The non-bonding pairs of electrons or lone pairs are placed on the outside. So we're going to look at this in more detail here. All right, so we did draw some Lewis dot structures in chapter 4, where we looked at the number of valence electrons. We looked at the group number, and then we drew our dots around the atom. So here it says, draw the Lewis structure for a fluorine molecule F2. So the first thing that we're going to do is determine the number of valence electrons. So we have two fluorines here. We have F2. So each fluorine is in group 7A, so that we are going to have 7 valence electrons from one fluorine plus 7 valence electrons from another fluorine for a total of 14 valence electrons. Then what we need to do is determine the connectivity of the atoms. So here we just have 2 atoms, so it's pretty easy to determine the connectivity. So we can draw the 2 fluorines next to each other. Then what we're going to do is arrange the remaining electrons so that each atom has a complete outer shell. Okay, so you're arranging the electrons so each atom has an octet. So let me just draw this for you over here. So we have our 2 fluorines. We're going to draw 2 electrons between them because there's a bond between them. Now we're going to arrange the remaining electrons so that each atom has an octet. All right, so this first fluorine, I'm going to just change my color for a minute here, now has 8 valence electrons. 2, 4, 6, and then 8. This second fluorine also has 8 valence electrons. 2, 4, 6, 8. Now let's make sure the total number of electrons present equals 14. We need to make sure of this because our Lewis structure cannot violate the total number of valence electrons. So we have 2, 4, 6, 8, 10, 12, 14. So we've drawn a good Lewis structure. Here you can see that the shared electrons are represented by a bond. All right, so when you're drawing a Lewis structure, you can either use the 2 dots or you can use the bond to demonstrate the shared electrons. I prefer the bond approach. You typically see that in organic chemistry, but you can choose which representation suits you best. So we've looked at 2 examples where you have the same elements or atoms bonded together. We saw this with H2 and F2. These are called diatomic molecules. The elements hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine exist as diatomic molecules. They exist this way instead of as a single hydrogen or a single fluorine because they are more stable bonded together where the electrons are shared than when they are alone. All right, so now let's draw a Lewis structure when we have a little bit more of a complicated molecular formula. Here we have CH4. Now, I said to you, the first stage of this process, we need to determine the total number of valence electrons. All right, so for carbon, it is group 4A. There are 4 valence electrons. For hydrogen, it is group 1A. There's 1 valence electron, but we have 4 of them. So we need a total of 8 valence electrons. Now, determining the connectivity, that's step 2. So in a previous slide, I talked about how the total number of valence electrons typically leads you to how many bonds that element or atom will form. All right, so let's take carbon for example. Carbon has 4 valence electrons. It needs 4 more to reach an octet. So carbon will form 4 bonds. Hydrogen has 1 valence electron. It only needs 1 more to form its, not octet, but it just needs 1 more to make 2, so it has the configuration of helium. So hydrogen only forms 1 bond. So in order to connect these, the carbon has to be the central atom with the hydrogens arranged around it. So you're going to draw the carbon and then the hydrogens, and then you're going to make the shared pairs of electrons. Now that third step, we needed to make sure that we're not exceeding that total number of valence electrons. So let's count. We have 2, 4, 6, 8. I'm sorry, the third step was to make sure everything has an octet. Well, everything has an octet here. We have 8 valence electrons total, so our Lewis structure is good. Now, again, we can represent it with just the dots or the bonds. I prefer the bonds when we have what are called bonding electrons that are between atoms. Okay, so for me, the bond is preferred, but if you like the dots, you can use the dots. All right, so table 6.13 shows you Lewis structures for some molecular compounds. Let's just look at NH3 before I move on. All right, so nitrogen is in group 5A. And then we have hydrogen, okay, again in group 1A. Now, there are 5 valence electrons for nitrogen, 1 valence electron for hydrogen, times that by 3. So we need a total of 8 valence electrons. In order to achieve an octet, nitrogen needs 3 more electrons. So nitrogen typically forms 3 bonds. We discussed hydrogen already. So when we're drawing this, we have nitrogen, hydrogen, hydrogen, hydrogen. We need to draw a shared pair of electrons, okay, between each atom. Then we need to give everything an octet. So we're going to draw 2 more electrons onto that nitrogen so it has an octet. Then we're going to count to make sure we haven't exceeded our total number of valence electrons, and we'll see 2, 4, 6, 8. Okay. The blue electrons are your bonding electrons. All right, so in a previous slide, we mentioned non-bonding electrons or lone pairs. So when the pair of electrons is not shared between 2 atoms, it is not part of a bond. It is called a non-bonding pair of electrons or a lone pair, and that's what's shown in red. Okay. All right, so now let's talk about double and triple covalent bonds. A double bond occurs when atoms share 2 pairs of electrons. All right, and this forms when there are not enough electrons to complete the octets. A triple bond occurs when atoms share 3 pairs of electrons. And this forms when there are not enough electrons to complete octets. So we're going to look at this in some specific examples. All right, so let's draw the Lewis structure for carbon dioxide. So the first thing we need to do is determine the total number of valence electrons. So carbon is in group 4A, so that's 4 valence electrons. Oxygen is in group 6A, so there are 6 valence electrons and we have 2 of them. So our total number of valence electrons is going to be 16. Okay. Then we need to determine the arrangement. Now, carbon, 4 bonds. It needs 4 more electrons to complete its octet. Oxygen likes to form 2 bonds. It needs 2 more electrons to complete its octet. So the arrangement is going to be the carbon in the center with the 2 oxygens adjacent. All right, so here we have our total number of valence electrons. Now, what we're going to do is we're going to draw in the bonded electrons. Or again, you can have them as bonds, whatever you prefer. Next, we need to add the remaining electrons so that everything has an octet. So I'm going to just draw those in. Now let's count. Let's see if we have the correct total number of valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have way too many. Right, but everything has an octet. So what are we going to do? So what we're going to do is we are going to remove lone pairs and make an additional bond. All right, so let me do that down here for you. So let's draw our carbon in the center with our 2 oxygens and our bonds. Now, I'm going to just draw the lone pairs in, and then I will erase them. All right, so what I'm going to do is I'm going to remove 1 lone pair from the oxygen and 1 lone pair from the carbon, and then I'm going to make a new bond. Now let's see, does everything have an octet? Let's count again. 2, 4, 6, 8, 10, 12, 14, 16, 18. I still have too many. All right, so let's try this again. All right, so let's remove a lone pair from carbon and a lone pair from oxygen and make a new bond. Okay, let's count. 2, 4, 6, 8, 10, 12, 14, 16. All right, so there's my structure. So what we did here is we made a double bond where we share 2 sets of electrons. There's 2 electrons in this blue bond and 2 electrons in that green bond for 4 electrons between those 2 atoms. And you can see carbon has 4 bonds. Oxygen has 2 bonds. Okay? In addition, oxygen has 2 lone pairs. Those are those non-bonded electrons. All right, so I always like to say, when you have a rule, there's always going to be an exception to that rule. So there are exceptions to the octet rule. Hydrogen just requires 2 electrons to form a noble gas. There are certain nonmetals that can form compounds with 10 or 12 valence electrons. Sulfur has an octet in many compounds, but sometimes it has 12 valence electrons or 6 bonds to that central sulfur atom. We are not going to deal with these exceptions. We are only going to work within the bounds of the octet rule. The only exception that we will see is for hydrogen, where you have just 2 electrons. All right, so for whatever reason, I don't have the PDFs for the slides here for section 6.7, but we're going to go through it. All right, so 6.7 looks at electronegativity. And bond polarity. And what we're going to do here is we're going to use the electronegativity to determine the polarity of a bond. Now, electronegativity is the ability to attract the shared electrons in a chemical bond. So it's going to be the affinity of an atom for electrons when they're making a covalent bond. The most electronegative atom is fluorine. So there is a scale assigned to electronegativity that ranges from 0 to 4. Fluorine is the most electronegative atom given a value of 4.0. Electronegativity is going to increase as you go from left to right on the periodic table. So across a given row, electronegativity will decrease when you go from top to bottom in a group. All right. So what we're going to do is use these electronegativity values to determine the polarity of a bond. All right, so remember, we're dealing with covalent bonds where you have a sharing of electrons. There are different types of covalent bonds. We are going to have nonpolar covalent bonds and polar covalent bonds. When you have a nonpolar covalent bond, the atoms are identical or have similar electronegativities. When you have a polar covalent bond, there is a large difference in electronegativity values. So the range for determining a nonpolar covalent bond is, all right, so if you take the difference in electronegativity between two atoms of a bond, and that difference is between 0 to 0.4, you have a nonpolar covalent bond. If the electronegativity difference is 0.5 to 1.8, you have a polar covalent bond. And then if that difference is 1.9 to 3.3, you have an ionic bond. You can find this in table 6.14 of your text. So let's just look at this practically, and you'll be given electronegativity values. Let's revisit our molecule CH4. And we want to determine if this is a polar covalent bond. What we'll do is we will look up the electronegativity of carbon, which is 2.5. And then we're going to look up the electronegativity of hydrogen, which is 2.1. And when you subtract them, you see the difference is 0.4. So this is a nonpolar covalent bond. All right, let's take another molecule. Okay, so here, I have a chlorine substituted for a hydrogen. We'll go through the nomenclature for this compound when we name organic compounds. All right, so if I ask you what type of bond is this, is it nonpolar covalent, polar covalent, or ionic, what you'll do is you'll look up the electronegativity of carbon, right, which we know is 2.5, and then you'll look up the electronegativity of chlorine, which is 3.0, and 3.0 minus 2.5 equals 0.5. So this is a polar covalent bond. When you have a polar covalent bond, this means that the electrons are not shared equally. they are going to reside closer to one atom of that bond. Now, the more electronegative the atom, the closer the electrons are. So, if we were to look at where the electrons would be closest, we would see that they would be closest to this chlorine. So this chlorine would have what's called a delta negative or a partial negative charge. All right, so this symbol here is a delta. The carbon, on the other hand, would have a partial positive charge. Because that chlorine would be pulling electrons toward it. So if we were to draw the direction of the electron pull, we would have an arrow with that dash at the end, right, indicating that the electrons are being pulled towards that chlorine. This charge separation creates what is known as a dipole. Where you have a partial positive and a partial negative. This is going to be important when we look at intermolecular attractions and the shape molecules take. So now what we're going to do in this section, and I know this is a long video and I'm sorry about that, but what we're going to do is we're going to take what we learned about Lewis structures and bond polarity and use that to predict the shapes that molecules assume. So it's important to learn about the shapes of molecules because the shape is important in how a molecule will interact with an enzyme or a protein. Right? The whole theory of molecular shape is going to be based upon what's called valence, shell, electron, pair, repulsion, also known as VSEPR. So when we were looking at bond formation, we looked at the fact that two nuclei can only come within a certain distance of each other, right? Because then they're going to repel each other. Those positive charges will repel each other. So again, let's just draw our hydrogens. Okay. So there is a positive charge. Let me just change the color. All right, for that nucleus, and another positive charge for that nucleus. So they can only get to within a certain distance. The same holds true for those two electrons, right? These two charges are similar. And they can only get so close to each other, and then they become repulsive. So what we're trying to do when a molecule assumes a certain shape is we're trying to minimize the repulsion of those valence electrons. So let's look at carbon dioxide. All right, so here we have our central atom carbon, and it is bonded to two oxygens. These oxygens can be referred to as electron groups. The repulsion between these two electron groups is minimized by placing them on opposite sides of the carbon. This will give the molecule a linear arrangement with bond angles of 180 degrees. So when you have a central atom with two electron groups, you assume a linear shape. All right, now let's look at what happens when we have three electron groups. All right, so we have a molecule known as formaldehyde. It has the formula H2CO. For this type of molecule, I'd give you the connectivity. Right? You should know, though, from our previous discussion that carbon forms 4 bonds, so it is most likely to be the central atom. Right? Let's draw the Lewis structure step by step before I jump into the shape, just so that we can have some review. So carbon has 4 valence electrons. Oxygen has 6. There are 2 hydrogens, that's 2. That's going to give us a total of 12 valence electrons. carbon needs to be the central atom, and then it is going to be bonded to a hydrogen, hydrogen, and oxygen. Let's draw in our single bonds. Let's give everything an octet. We'll put a lone pair on carbon, the lone pairs on oxygen. Our hydrogens are satisfied because they only need 2 valence electrons. Let's do our count. We'll see we have 2, 4, 6, 8, 10, 12, 14. We have too many. So what we're going to do is we're going to have to take away some lone pairs. All right, so we have carbon, hydrogen, hydrogen, oxygen. Let's make a double bond, and then we'll put 2 lone pairs on the oxygen and no lone pairs on the carbon. Let's do our count. 2, 4, 6, 8, 10, 12. All right, we've satisfied our count. So this is why this is our valid Lewis structure. If we look at our central atom, this carbon here, we can see it has 3 electron groups. It has an oxygen, a hydrogen, and a hydrogen. In order to minimize repulsion between these 3 groups and place them as far apart as possible, the bond angles will be 120 degrees. When you have a central atom with 3 electron groups, we assume a trigonal planar shape. In a molecule of SO2, sulfur dioxide, there are also 3 electron groups. However, the 3 electron groups are different than the 3 electron groups that we saw in formaldehyde. You can have a single bonded oxygen atom, a double bonded oxygen, and a lone pair of electrons. In order to minimize repulsion, you will have a bent shape here. Okay. The bond angle is still 120 degrees. So it is still a trigonal planar geometry. However, the molecule has a bent shape because there is a lone pair here on the sulfur, and it does not have a 3rd bonding group. For our purposes, when you have something that's trigonal planar, there will be 3 bonding groups, similar to what we saw in that previous slide. Now we're going to look at central atoms with 4 electron groups. So we've already drawn the Lewis structure for CH4, which is also known as methane. And you can see the structure here. In order to minimize the repulsion of these 4 groups, they are going to be arranged in a tetrahedron with bond angles of 109 degrees. So the shape with 4 bonds on the central atom is called tetrahedral. Right, so know that when you have 4 bonding groups, you have a tetrahedral arrangement with a bond angle of 109 degrees. All right, now we're going to look at when we have 4 electron groups, but one of those electron groups is a lone pair of electrons. So what we're going to see is that we have 4 electron groups. Okay, 3 are going to be bonding, and 1 is going to be non-bonding. All right, that is the case for NH3, and we already went through on how to draw the Lewis structure for NH3. So in order to minimize repulsion, you're going to place the bonding groups with bond angles of 109 degrees. Actually, to be accurate, they're going to be around 107 degrees. So they're going to deviate slightly from that 109. Okay. The shape is going to be a trigonal pyramidal. Right? So this one you have to remember that when we have 4 electron groups, 3 of which are bonding and 1 of which is non-bonding, we assume a trigonal pyramidal shape. And that bond angle is going to deviate and be 107 degrees. The reason why it deviates is because this lone pair is going to push those bonding groups away, right? Because they're going to be repulsive, so the lone pair is going to make them actually push away more. All right, the next configuration we're going to look at is when we have 4 electron groups again, but now we're going to have 2 bonding and 2 non-bonding. When this happens, okay, you're still going to have a tetrahedral shape, but now you have two lone pairs that are going to really push down, and they're going to make what's known as the bent shape. And here the bond angle is going to be around 105 degrees. All right, so let's go through this and summarize. When you have two electron groups, you have a linear shape. Your bond angle is 180 degrees. When we have three electron groups, and they are all bonding, you are going to have a trigonal planar shape. And the bond angle is 120 degrees. When you have four electron groups, all are bonding, you have a tetrahedral shape, and the bond angle is 109 degrees. If you have three bonding and one non-bonding, you have a trigonal pyramidal, and your bond angle is 107 degrees. And then if you have two bonding and one non-bonding, you have a bent shape, and your bond angle is 105 degrees. So these are the bond angles and geometries that you need to be responsible for. Okay, so this table is just summarizing what I just wrote down in my chicken scratch. I'm going to cross out this one. You don't need to know that one. Okay? So just keep that in mind. I spelled pyramidal wrong. I'm sorry. If we were in class, you would see I'd make tons of spelling errors when I'm writing on the board because my brain is faster than my hand. Again, all of these shapes result from trying to minimize electron repulsion. All right, so now let's try and predict the molecular shape. We have the formula H2S. You should be able to name this compound. All right, the name of this compound is dihydrogen sulfide. All right, let's draw the Lewis structure. We need to determine how many valence electrons we have. All right, so hydrogen has 2, sulfur's in group 6A, it has 6, so we need a total of 8 valence electrons. Sulfur needs 2 more electrons to achieve its octet. So sulfur will make 2 bonds and will be the central atom. So we'll have sulfur, hydrogen, hydrogen. Let's add our electrons so that everything has an octet. Now let's count. 2, 4, 6, 8. So we have our valence electrons, so our structure is acceptable. Now let's look at sulfur. I'm going to just redraw this for us. We have 4 electron groups, 2 of which are bonding and 2 are non-bonding. So this means that there is going to be a bent shape, and the bond angle is going to be 105 degrees. All right, so this just has everything typed up nicely. You have around the central atom, you have a bent shape, right? And it didn't make you give the bond angle, but I gave it to you anyways. All right, let's do a learning check. State the number of electron groups and lone pairs and use the VSEPR theory to determine the shape of the following molecules or ions as tetrahedral, trigonal pyramidal, or bent. Pause your video and determine this. Alright, so for the first one, for A, we have PF3. Phosphorus is found in group 5A. There are 5 valence electrons. Phosphorus is going to want to form 3 bonds. Then we have fluorine, which is found in group 7A. It has 7 valence electrons. It only needs 1 more to make an octet, so fluorine is only going to form 1 bond. So your phosphorus is going to be your central atom. Okay, and we're going to need a total of 26 valence electrons. So let's put our lone pairs in. And let's count. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we've got our valence electrons. Now let's look at phosphorus. Phosphorus has 4 electron groups, 3 of which are bonding, 1 is non-bonding. So your shape here is going to be trigonal pyramidal. Let's do the same thing for H2S. Well, we've already gone through H2S. All right, so here the shape is going to be bent, and you have 2 bonding and 2 non-bonding groups. And then finally we have CCl4. Now, carbon has 4 valence electrons. It forms 4 bonds. Chlorine has 7 valence electrons, so times that by 4. All right, it's going to form 1 bond. Our total number of valence electrons, 28 plus 4 is 32. Carbon is the central atom. All right, if you count, you'll see we have 32 valence electrons in this configuration. Carbon has 4 bonding groups attached to it, so it is a tetrahedral shape. All right, so this is just stepping you through what I just did. All right, we have the Lewis structures. All right, you're going to arrange the electrons around the central atom. So for PF3, H2S, and CCl2, they all have a tetrahedral arrangement. However, all right, because you have a lone pair on PF3, it is going to be a trigonal pyramidal. Because you have 2 lone pairs on the sulfur, it is going to be bent. And because we just have bonding groups on the CCl4, it will assume a tetrahedral shape. All right, so again, I know this video was long. There's a lot of information here. But everything that we did builds to where we can predict molecular shape using our Lewis structures.